Black holes are among the most fascinating and mysterious objects in the universe. They're regions of space-time where gravity becomes so incredibly intense that nothing can escape from within their event horizon, not even light itself. But not all black holes are created equal. There are actually several distinct types of black holes that form in different ways and possess different characteristics. Understanding these categories helps us grasp the incredible diversity of the cosmos.
The first and most common type is the stellar black hole. These form when massive stars, typically at least 20 times the mass of our Sun, reach the end of their lives. When such a star exhausts its nuclear fuel, it can no longer support itself against its own gravitational pull. The star collapses catastrophically inward in what's called a supernova explosion. If the remaining core is massive enough, it collapses completely, forming a black hole. Stellar black holes typically have masses between 5 and 20 solar masses, making them relatively small but incredibly dense. The second type is the supermassive black hole. These objects are millions or even billions of times more massive than our Sun. They're believed to exist at the centers of virtually every large galaxy, including our own Milky Way. The black hole at the center of our galaxy, called Sagittarius A star, has a mass of about 4 million suns. How supermassive black holes formed remains one of astronomy's greatest unsolved mysteries. One theory suggests they grew from smaller black holes through countless mergers and by consuming vast amounts of surrounding matter. Another possibility is that they formed directly from the collapse of massive clouds of gas in the early universe. What's remarkable is that despite their enormous mass, supermassive black holes can have surprisingly low density near their event horizons. Intermediate black holes represent a third category. These objects fall between stellar and supermassive black holes in terms of mass, typically ranging from 100 to 100,000 solar masses. For many decades, astronomers debated whether intermediate black holes actually existed at all. Recent observations, particularly from gravitational wave detectors, have provided evidence for these elusive objects. They may form through the merger of smaller black holes or through unusual stellar processes in dense star clusters. Primordial black holes are a theoretical fourth type that would have formed in the very early universe, mere fractions of a second after the Big Bang. These hypothetical objects would have been created from density fluctuations in the primordial plasma. Unlike other black holes, primordial black holes could potentially have any mass, from incredibly tiny to extremely large. If they exist and haven't evaporated through Hawking radiation, they could be flying through space today. Scientists are actively searching for evidence of primordial black holes, as they could potentially explain some of the mysterious dark matter that makes up much of the universe. Extremal black holes represent another theoretical classification. These are black holes that rotate at the maximum possible speed allowed by the laws of physics. An extremal black hole would have an angular momentum equal to the maximum value permitted by general relativity. Physicists debate whether such objects can actually exist in nature, or whether they're purely mathematical constructs. Kerr black holes are rotating black holes that form in the real universe. Most black holes probably rotate to some degree. A Kerr black hole has two event horizons and an ergosphere, a region where space-time itself is dragged around by the black hole's rotation. This makes Kerr black holes significantly more complex than non-rotating Schwarzschild black holes. The physics near a rotating black hole becomes extraordinarily intricate and fascinating. Raisen and Nordstrom black holes are theoretical black holes that carry electric charge. In the real universe, charged black holes are believed to be extremely rare because any charge would likely be neutralized by surrounding plasma. However, studying charged black holes helps physicists understand the mathematical structure of general relativity and the nature of space-time near extreme gravitational conditions. Finally, we must mention black holes of different spin types and merger products. When two black holes merge, they create a new black hole with properties determined by the masses and spins of the original objects. These merger events produce gravitational waves, ripples in spacetime that we can now detect with sophisticated instruments. Each type of black hole teaches us something different about the universe and the extreme conditions that arise from gravity's power. The study of black holes bridges observational astronomy, theoretical physics, and pure mathematics, making them endlessly fascinating.